operationalize it and synthesize in such a way that they can be a perfect semiconducting chip. And here we have few instruments that we use for it. Glove box is used for basically synthesis and the fabrication of the devices to make sure that no oxygen is trapped in between. And once they are in, once the final thin film layer is prepared, we take it out, and after that it is quite stable in the ambient environment also. And here we have a thermal evaporator along with the glove box. So directly after metallization, we can collect the chip in the glove box area and characterize there, or take it out and use for characterization setup here.
So, what is a memory, sir? You might ask. Basically, what this lab is expertise is to prepare a kind of artificial neurons. Just like how brain thinks, our brain has neurons and they are connected through synapses, right? So here they are creating a metal, then a dielectric insulator, and then metal structure. And for that structures, they are using different materials, which might be oxygen sensitive, humidity sensitive, atmosphere sensitive. And when you have such sensitive material, we use glow box where we put the nitrogen or argon gas, inert gas inside, so there is no oxygen inside the chamber, and they prepare the layers and they study outside. Now some materials they do not get affected by oxygen or atmospheric humidity, they can be prepared outside on that particular station. And if you need to do some chemical processes, then we have the chamber over here for chemical processes, and we have different instruments, as you can see, for different preparations. So here basically we use spin coating technique, where you prepare, if your material is dissolvable in some solvent, you can use the spin coating technique. If your material is inorganic, which does not get dissolved, like ceramic material or it's metallic material, you want it as it is, then we have sputtering instrument, and we have pulse laser deposition setup, where we use our material and we make it target, and then we create a plasma, in situ plasma, hold it, and this plasma's kinetic energy is transferred into the material's kinetic energy. It is stationary, it's a complete momentum transfer, they get ejected, and over a substrate we deposit the film. Here we can control the film thickness from tens of nanometers to micrometers. So generally all of our students and our groups are working at nanometer thickness. So it could be bifurcated at nanofilms as well as thick film, thin film and thick film. And these devices are not only used for memory, here we are also preparing sensors, thermoelectric devices, magnetic devices, and other types of devices. Here this facility enables us to have a good quality fabrication, good quality of analysis. Now this instrument that Janice explained, some of you might be able to see the graph. If he can explain, this is a butterfly kind of behavior, right? So this is where the energy is getting stored. So in multiple cycles, you can see, you see the graph, what we know is the voltage versus current, right? So there is a 0 volt, then you have plus 2 volt and minus 2 volt. So they give a pulses of few volts, like 0.01 volt. So you give a pulse of 0.01 volt for 10 milliseconds, and you observe, is there a change in the current? And you keep on observing this pulses of voltage, and you keep observing the current. What happens? As per the Ohm's law, we expect that if it is a metal, if it is a conducting, it has to follow linear path, right? But since it's a kind of a semiconductor material, based on the mechanism, it will follow some non-linear path. So now it will be I could be proportional to V, I could be proportional to V to the power 1 by 2, or some logarithmic of the voltage. So those behaviors are getting observed over here. Based on that, we are trying to understand what kind of mechanisms are happening in a material. And then you try to fine tune by thickness thickness optimization, or its electron transport layer, hole transport layer optimization, and you try to optimize as large gap as possible. Why? Because once you follow from 0 volt to 2 volt, while you start reducing the voltage, the same path is not followed. The current is following the second path, not the same path. So there is a hysteresis here. The hysteresis of the voltage is observed, right? And that's when we say now, okay, so earlier we took a path of high resistance, but since it is coming back through higher current, not the lower current, that means resistance has dropped. So we call it low resistance state. So they optimize the device in such a way that current follows from high resistance state to low resistance state. Now you see the current is in microampere and voltage is in the voltage range. Now if we want to look at the power consumption, so P is equal to ID. That's the simplest idea that we can do. So here if it is 25 microampere at 1 volt, then it is 25 microwatt. We can say is the consumption. They can also optimize to nano ampere and low voltage like 0.5 voltage cycle. And then we have consumption per memory device is of nanowatts. So if we have 1 billion such memory components of nanometer thickness, then we have hardly consumption of 1 volt to think for this device as a brick. So this is a kind of an futuristic architecture where instead of coding machine learning, this device itself is the machine learning.